Hi everyone, in this video we are going to continue talking about log functions, and we've done the previous objectives in the last video, so we're going to be graphing logarithmic functions in this video. Let's begin by talking about some of the properties of a log function, and I want to remind you, if you can go back and look at your exponential functions and those properties, then you're going to find that a lot of this looks very familiar, and that's because a log function is the inverse of an exponential function. So if this is f, the log function is f inverse. And so remember, with functions that are inverses of each other, everything pretty much just switches. And so we are going to have a lot of similarities here. So you'll see what I'm talking about. The domain of a log function is 0 to infinity, and the range is all real numbers. For our exponential function, the opposite was true. For a log function, we have an x-intercept at 1, so 1 comma 0. For the exponential functions, it was the y-intercept was 0 comma 1. And this one, the properties for logs is that there's no y-intercept. Then we have a vertical asymptote on the graph of a log function at x equals 0, the line x equals 0, which is just the y-axis. On the exponential functions, we had a horizontal asymptote, which was y equals 0, or the x-axis. And then a log function is decreasing if your base is between 0 and 1, and it's increasing if the base is greater than 1. And then the graph contains these 3 points. So I think in the previous video I labeled this one as 1, and then this one was 2, and then this one was the third point. Notice they're the exact opposite of the points from our exponential function. So we have -1 as the y value, and then 1 over a is the x value. It was the opposite for the exponential function. And then 1 comma 0 and a comma 1. And then we have a smooth continuous curve. Alright, so here's both of the functions, and depending on the base as well. So we have the exponential function in blue, so exponential is in blue, the log functions are in red. So the first graphs are for a base between 0 and 1, and then the second graphs are for a base greater than 1. So the blue is what we learned last time. So remember how that went. We had an exponential function that was decreasing, going down to the right, and now we have our log function that as we plug in greater x values, it's actually still going down. But remember how this works with inverse functions. So a quick reminder, and again we learned this in the past, so inverses, they have symmetry. So the graphs are symmetric. So symmetry about a specific mirror line, and it's the line y equals x. So this line right here in the middle is the mirror, and so if you have one graph, the inverse just flips over that line. So every point on the top flips over to the bottom and vice versa. Then your other one here, our exponential function in blue, the base being greater than 1, it's rising or going up, increasing to the right. Then our log function is also actually doing the same. It's going up toward the right. And notice they are reflected across that mirror line. So every point that was on the exponential function gets mirrored over the line y equals x to form the log function. So sort of a zoom out for you on this, because these graphs are a little zoomed in. This is what it would look like for most of the time when you see these log functions. They look a little bit more like this. Okay, so the graphs are just a little zoomed in here. So this one would look a little bit more like that. Just so you're aware, we do have a vertical asymptote at the y-axis on both of these. Okay, so now a reminder of the ln function. So we learned this in the last video, but natural log is log base e. So we use ln for natural log, and it's log base e. If it helps you, feel free to rewrite ln as log base e every time if you want to see what the base is, but just so you know that that's what that represents. And if you go to exponential form, remember how that works, we did this last time, whatever the log equals is the exponent. So whatever's on the other side of this equal sign, that is the exponent for your exponential statement here. And so the base here is invisible e right there. So that's still the base here. So it says e to the y power equals this argument of x. So we went through that last video, just a quick reminder on how that works. This is the graph of our exponential function with base e. It's called the natural function, but this is the natural log function. So this is the graph of the natural log function in red. And remember, e is just approximately 2.718. Now let's go ahead and work through a few examples where we graph these log functions and also its inverse function. So our function here is going to be natural log, but negative a natural log of x plus 1. So just again, this is the same thing as saying negative log base e, and then our argument is x plus 1. If that helps you, feel free to rewrite it that way. So we're going to graph that function after finding the domain, and then figure out the range and the vertical asymptote, and then we're going to find the inverse function, find the domain and range of that, and graph that as well. But it's going to be fairly straightforward to do the work with the inverse function after we figured out all of the steps for the original function. Alright, so the domain, remember from when we first learned about logs in the last video, the argument of your function has to be positive. So in our case, we had natural log, the argument was plus 1, x plus 1, so you just set x plus 1 greater than 0, and then solve. So x has to be from negative 1 to infinity, not equal to negative 1, so parenthesis there. Now to graph this, notice we have transformations going on. There's actually 2 of them. So remember this transformation in the front, this is like saying negative f of x, and so that's going to be a reflection across the x-axis, so like a flip. And then this part here, this is happening in here with x. This is like saying x in f of x plus a number, and so that's actually a shift left. That's a horizontal shift. So those are our 2 transformations. So using the original graph, this is our original graph here, natural log of x, and just plotting the 3 main points that we know. We have 1, 0, e, 1, and 1 over e to the and then negative 1. And those are from the 3 points that are on every graph. You just fill in the base. In this case, the base is e, where we used to have an a. But just a quick side note, you can always plug values in for x and just do an xy table. So when in doubt, you can always plug numbers in. So if we plug in 0, we say natural log of 0. What does that equal? And then it usually helps to put it in exponential form to solve that. So to solve it, I would say something like e to what power equals 0. And so that only way to get a 0 there would have to be a power of 1. So that's how I get that point. Let me just do one more. If I wanted to plug in a 1 here for x, well, that'd be a little bit difficult because I would be asking myself natural log of 1, or in other words, e to what power equals 1. So instead, what I want to do for x is I want to pick, that one I can use a calculator, but for this I'm going to pick e for x. And so if I say natural log of e, that means e to what power equals itself. And so that has to be the power of 1. And so that point is e, 1. And I can do that with other values for x as well. Okay, so that's one way to graph it if you don't just use your 3 points you know are on the function. So from there, from the original, we know that we're going to flip or reflect the whole graph across the x-axis because of that minus in the front right there. So all of your points flip over. This one is still on the x-axis, but the other 2 points, this was negative 1, but now it's up here at positive 1, and this point was at positive 1, and now it's down at negative 1. And then the next transformation is because we had a plus 1, x plus 1 inside here, we actually move 1 unit left. So all of our points move over left, just 1. So our x value used to be 1 over e. So now that's 1 over e and then minus 1. You can use a calculator to get that number if you'd like. And then what was at 1, 0 is now at 0, 0. And then what was at e is now at e minus 1. And then that's the new graph. Notice also though that the vertical asymptote that used to be at 0, x equals 0, has shifted over, and the vertical asymptote is also shifted over 1. So it's at x equals negative 1. So then the range for this function is all real numbers, and you can tell if you go back, you can tell that the graph's going to go all the way up toward infinity forever here, and it's going to technically go all the way down to infinity. So that's the range. And then we just talked about the vertical asymptote at x equals negative 1. So now the inverse, we're going to go ahead and solve for that first, and then use our results to answer the other parts. So remember how inverse functions work. You swap x and y. Okay, so that's the first step. Here's your function. Okay, just put a y right here. And so that's our function. And we want to find the inverse. So inverse means you swap x and y. And then you actually want to do a little bit work and solve for y. Alright, so here's how you do this. And this is new. We haven't had to solve something like this just yet, but we can do it pretty easily based on things we've already learned. So the log part is already pretty much isolated. We could go ahead and divide out that negative. And so let me do that. I don't have it here, but let's put it there. So I'm going to divide out the negative. So that's actually going to turn positive. And then how did we get here? So from here to here, this is from what we learned previously. Let's rewrite this. So we know, then let's do it in steps. We know the following is true. If we have log base b of x equals y, exponential form says that that's b to the y exponent. That's how you get x. So that's exactly what just happened here. So if we write this out in a little bit more detail, this says negative x equals log base e of y plus 1. So my base is e, so I have e to the power on the other side of the equal sign. Let's change colors. So whatever the log equals is the power. So that's going to go here. And then the argument is just what this exponential function equals. And so that's how we go to exponential form, using our definition that we learned previously. Okay, so that's required when you're trying to solve for y here in this argument. Okay, so now we're just a couple steps away. Just subtract 1 from both sides, and then go ahead and write it as your inverse notation. So rewrite the y part as f inverse. So f inverse of x is e to the negative x minus 1. And so this equation here is the opposite, or the inverse, of this equation here. Now the domain of the inverse, the nice part is that it's just the range of the original. So that was all real numbers. So the domain of f inverse is just all real numbers. And then the range of the inverse is just the domain of the original, which is negative 1 to infinity. So we've already did the work for the original, so we just use that information to swap it for the inverse. And now to graph this, again, we've already done the work, so all we do is we switch everything. So our original function was in blue, so the original is over here in blue, and everything switches. So where this point right here was, and I mean original as far as the after we transformed it. So the new original after we transformed it. So we had this point here where the x value was 1 over e minus 1 and the y value was 1. We switched those. So now the point is 1 comma 1 over e minus 1. So the x's and the y's switch from the original function to the inverse function. You just swap your points. And again, they just reflect over this line, y equals x or x equals y. That's your mirror line right here in the middle. And so you do that for all your points. 0, 0 is the same if you switch it or not. And so now you just swap your last point here, and that is your new graph, the green one, the inverse, but also what you want to switch is the asymptotes. So the log function had a vertical asymptote at x equals -1. So the exponential function is going to have a horizontal asymptote at y equals -1. So make sure you swap the asymptotes as well. Alright, let's take a look at one more, and this one is our common logarithm function. And we talked about this in the last video as well, but if you see log with no base, it really means log base 10. And so this is called the common log function because it's so commonly used for the base to be 10 that we just tend to not write it. So if it's missing, it's base 10. Also, what was mentioned in the last video was that the log button on the calculator means log base 10. And so this means 10 to what power equals x. So let's do one more example with graphing, and we're going to graph this logarithmic function to log of x minus 2, and then we're going to talk about the domain, and then find the range and vertical asymptotes, and then also work with the inverse function. Alright, so remember that the argument has to be positive, so you just set your argument greater than 0, and then solve. So the domain for this function would be 2 to infinity, not including 2. Then for the graph, let's use our transformations like we did on the last example. Notice that there are two transformations we are going to apply. Right here, this timesing by 2, multiplying by 2 is going to be a vertical stretch, and then this minus 2 inside with x is actually going to be a horizontal shift, and it's going to make our graph go to the right 2 units. Here is our original function, log of x, or log base 10 of x, and we just plot a few points on that one. 1, 0, 10, comma 1, and then 1/10, comma -1, and then we will apply our first transformation. We will shift the graph 2 units right by replacing that argument of x with x minus 2. So all of our points just moved over 2 units to include the vertical asymptote. So make sure that you shift the vertical asymptote over 2 units as well. It used to be on the y-axis, x equals 0. Now it's the line x equals 2. And then from there, we'll apply our last transformation, multiplying the whole function by 2. And so all of your y values essentially get multiplied by 2. So it's a vertical stretch. So this one's still at 3, 0. And then what was 12, comma 1 is now 12, comma 2. And then this y value moved down to -2. So that's going to be the graph of our log function. Okay, so the range is all real numbers, you could tell from the graph. And the vertical asymptote, that shifted over, so we got that x equals 2. So now we want to find the inverse of this function. So just like on the last example, we're going to swap x and y. Where there was a y, put an x. Where there was an x, put a y. And then we will solve for y. Very first thing we do have to do is isolate the log term. So just divide both sides by 2. And then we're going to go to exponential form. So remember, this is just, you can even say 1/2 x on the left. And this is log base 10 on the right. Argument is y minus 2. And so this says 10 to what power? The power being the other side of the equal sign, and it equals the argument. So that's changing to exponential form. And then we just have one more step, add 2 to both sides, and then write it as your inverse notation. This is the opposite or inverse of this function here. Alright, and like the last example, the domain of the inverse is the range of the original, which is all real numbers. And then we have the range of the inverse is the domain of the original, range is 2 to infinity. And then the graph, we'll just swap our x's and y values and our asymptotes. Okay, so here is the graph. We just take our 3 points that we plotted on the log function, and we swap them, the x and the y values, or mirror them over the line, y equals x, and then we also shift over the asymptotes. So the asymptote was this vertical one at x equals 2, so that's going to have a horizontal asymptote for our exponential function at y equals 2. Okay, so that's it for this one, graphing our log functions and then also finding the inverse, going back and graphing our exponential functions. So when in doubt, you can always just plot points by plugging into the function, but just remember that you have 3 main points that are on all of your log graphs, so this is a fast way to graph them. All right, that's it. Thanks for watching.